Okay, you can go.
Okay, so hello all. My name is Amitoz, and I'm doing my PhD in PDEs and variational methods on graph here at GREYC lab in Unicon with Amitoz and Julian Rava. And Abder is the one who works in PDEs on graphs, and Julia works on variational methods on graphs. And today I'm going to present our work on point cloud processing using GNNs. This is still an ongoing work, so a lot needed to be explored. And I hope that by the end of this presentation, you will have a fresh perspective on GNN and you will learn something new. So this is the outline of my talk. So in the introduction, I will briefly discuss on GNNs, message passing networks, and PDEs and variational methods on graphs. And then in the next section, we will make an interesting observation on how to implement PDEs using message passing networks. And then finally, I will talk on training GNNs to solve inverse problems on graphs. Okay, so why graphs? Because they can represent regular and irregular type of data, like images, point clouds, molecules, social networks. And graph neural networks are simply the neural networks which directly operate on graph structure. And at the core of many aforementioned GNNs is the term called message passing networks, which I suppose was first coined by the researchers from Google Brain, where in the paper called Neural Message Passing for Quantum Chemistry, where they proposed a new framework which reformulated many of the existing GNNs. So what is message passing? In simplest term, it is a generalized convolution on graphs. And the idea is to pass messages between nodes and agglomerate to define the node representations. Equation 1 is the message passing equation, and I hope that by now the audience is very much familiar with this equation. The F represents the signal, all the features on the nodes, and the superscript n-1 and n represents the layer, and the C and the phi are also known as the update function and the message functions. And very often they are multi-layer perceptrons. So PDEs and variational methods are two known and popular framework to address inverse problems on images. And these methods have been extended to graphs by defining the p-Laplace operator. And whatever the applications one can think in the domain of images can also be extended to graphs and hence point clouds via PDEs and variational methods on graphs. So let's look at equation 2, the optimization problem, and keep this equation in mind because I'll be referring to this equation a lot. So the problems of interest are the TV problem, basically the TV1 and the TV2, the total variation regularization. And the PDE way of solving this equation 2 is shown in the equation 3. And the delta here represents the Laplacian operator on graphs. And for the TV1 case, this becomes the anisotropic Laplacian. And for the TV2 case, this is the isotropic Laplacian. And for generalized P and Q settings, this is also called the p-Laplacian operator on the graph. One can observe that such way, this PDE way of solving the equation 2 will require some sort of epsilon so that you don't get division by zero error in the Laplacian. Apart from the PDEs, the two known way of solving the equation 2 is the Gauss-Jacobi, or also known as the Gauss-Seidel iterative scheme. And here also one can see that this will also require some sort of epsilon to avoid the division by zero error. The primal dual algorithm has also been extended to graphs, and this gives the most accurate solution because there is no such epsilon here. Okay, so let's make an interesting observation. The equation 4 here is the anisotropic diffusion on graph. So this is basically the equation 3, which I show the PDE equation with lambda equal to 1, and there is no data fidelity term. And equation 5 is the forward Euler method to solve the equation 4. And consider the message passing equation in 6. And it is easy to see from 5 and 6 that there is a one-to-one correspondence between the phi function, between the C function, and the square operator. So this, what does it mean? This is indeed an interesting observation, because this means that is PDEs on graphs can itself be thought of some sort of a message passing network, and vice versa. So from now, this example may be very elementary, where there is a one-to-one correspondence between the PDE and the message passing. But from our experience, even the more complicated PDEs or the variational schemes like Gauss-Jacobi and the primal dual can also be implemented using this message passing framework. But what happens is that one has to use the nesting of the message passing. That is, inside a one message passing, you are calling another message passing. So on a more practical side, what does it mean? It means that one can use the message passing framework from the taught geometric itself to do some PDEs and variational schemes on the graphs, and hence you can benefit the hardware acceleration. Okay, so this is one application of the equation 2, and the ambient PD here represents implementation of the primal dual with the message passing framework, and ambient GJ is the implementation of the Gauss-Jacobi with the message passing framework. And the bottom row here is just a solution of the functional in the equation 2 with the automatic differentiation module in PyTorch. But keep in mind that the equation 2, which I show the variation problem, was not a smooth problem. So one has to keep some epsilon approximation whenever we use the automatic differentiation. So this is particularly for the TV2 case. Here, the signal on the graph was just the XYZ value of the point cloud. And on visual assessment, many of the results looks very similar. But since PD, the ambient PD does not have any sort of an epsilon approximation, so it is the most accurate algorithm. And from our experiments, interestingly, on different graphs for the different for the TV2, TV1, and for the different schemes, we found that Adam was turning out to be the second best algorithm in terms of accuracy, even with the epsilon approximation. So here is another application of the equation 2, which is the point cloud denoising. So this is a large point cloud with 100K points, and this is the denoising with just 100 iterations using the TV1 diffusion, and it basically takes less than 0.3 seconds with the ambient PD ambient PD implementations, and with the other it roughly takes like 0.6 or 0.7. Okay, so let's have a look at the on the final section of this presentation on how to train a GNN to solve inverse problems on graphs. So the objective here is we try to do the TV regularization on the graphs using the GNNs with the objective of with keeping in mind the benefit of computation speed. And the way we accomplish is through unsupervised learning and model distillation. So what is unsupervised learning? In the unsupervised learning, the loss function which is minimized is simply the functional we saw in the equation 2. And what we do is we input the point cloud and the weights to the GNN, and the output is then fed into the equation 2, which is a non-smooth optimization problem, and which is then directly minimized using an optimizer. In the model distillation, what we do is we try to mimic the output of an ambient which is designed to solve a variational model, such as ambient PD. So we do this through the L2 through minimizing the L2 norm loss function, and the capital F here is the output of the ambient PD. And the GNN is trying to approximate the output of the ambient PD. One more thing, in this case, we don't need to have any sort of epsilon approximation because this is a smooth function, whereas the functional you have here was not smooth. So again, you will have to have epsilon approximation. Okay, this is the model architecture of the GNN being used for both the cases. It is a very simple architecture. If you are familiar with GNNs, it just has 3 MPN layers, and the MPN layer is very much inspired from the edge convolution in the DGCNN paper by Wang. So the message function is basically a multi-layer perceptron on the concatenated features, and the square operator is the sum, and there is no update rule. And just have a look at it. Okay, so we used the ShapeNet part dataset, which has around 17K point clouds at the size of around 3K each point cloud, and we create weighted KNN graphs, and it has 16 classes, out of which 15 were used for the training, and there was one holdout class which was not used for training. So that means it was completely unseen and then used for testing. And 20% of those 15 classes used for training were also used for validation. Okay, so here is a result showing the comparison of output of GNN with distillation, GNN unsupervised, MP and PD for the TV2 case, and recall that the test class is the one which was holdout during the training, so it's completely unseen during the training. So this whole pistol class was not seen. And apart from this pistol class, we also test on 2 other point clouds, which are basically not the part of the ShapeNet dataset. These, namely the bunny and the elephant. And one can see that they are able to match the output. The output is they are able to match the output of the MP and PD. Here is the result of the time comparison. So in this plot, we compare the time taken by the GNNs and the 2 most accurate algorithms, namely the ADAM and the PD. For the case of Adam and PD, it takes roughly a few seconds to get to the most stable and the converse solution, while the GNN yields its output in just 1.5 milliseconds, with the relative error of 1.2% for the unsupervised GNN and 2.2% for the GNN distillation. Okay, yeah. So, okay, I suppose that was the last slide. So, thank you for listening, and if you have any questions, we can discuss.